This video will focus on the learning target. It can calculate energy change for any thermochemical reaction if heat of reaction is known. The content for this learning target will be delivered over two videos, one that really focuses on the content and then one on the actual calculation. So in order to talk about heat of reaction, we have to understand what enthalpy is, because when we talk about the heat of a reaction, we're actually talking about the enthalpy of a reaction. So enthalpy is just another way to talk about the heat content of a system. And it's specifically the heat content of a system if pressure is being held constant. Essentially, the variable enthalpy is supposed to quantify both the heat done in a system as well as something called the work done in a system, which is something you guys will talk about in physics. And in the chemical world, the only time we have work done in a system is when the pressure is changing. And since in all our scenarios pressure will be held constant, enthalpy is just another way to talk about heat. Okay? So everything we know about heat so far is total energy, potential, and kinetic. That's what enthalpy is. The symbol for enthalpy is an H, capital H. You can think of it as representing heat. It always is the change in heat, though, delta H. The reason why it's a change in H is because it's really hard to quantify the heat of a system as it just sits there, especially a chemical system. Like how much energy the system actually has is hard to determine. But once it undergoes a change, like for example a phase change or a chemical reaction, or it dissolves, so once it goes through a chemical process change, we can quantify how much energy was either gained or lost. And that is what delta H represents. So delta H represents the change as it happens in a chemical process. So if you look down in that kind of purple pinkish box, you have a list of a whole bunch of different enthalpies that we're going to encounter. We have the enthalpies that relate to phase changes. So those are delta H of fusion or delta H of vaporization. So fusion or vaporization. We have the delta H of chemical reactions, which is delta H RXN for air reaction. We have the delta H of dissolving something, which is of solutions, or S. And then also something called the heat of formation, which is the energy associated with making any compound from its normal state elements. So when it comes to incorporating delta H into chemical processes, we create something called a thermochemical equation. And all this is an equation, so the chemical process, whether it's dissolving or reacting or phase changing, and the heat energy associated with that change. So instead of just including a heat symbol like we did at the beginning, like the triangle, we actually include the number this time. The number, standard-wise, is considered to be the amount of energy when that process is happening at 1 atm at 25 degrees Celsius, and the physical states must be given because the amount of energy change depends on what state it's in, right? A solid will give and take in a different amount of energy than a liquid will. So here's examples of what thermochemical equations look like. They're just normal chemical reactions, but they include a heat energy. So 890 kilojoules is the first example, 242 kilojoules is the second example, and those are the heat energies associated with these chemical processes. One thing you'll notice is for the combustion one, heat is a product, and for the electrolysis of water, heat is a reactant. Okay, when we think about that in relation to our signs then, endothermic, exothermic, when something is a product, that will be exothermic, so it'll be a negative heat energy released. And if something is endothermic, it'll be a positive heat energy gained. So when we write them in the reaction, we don't include their symbols, plus and minus, because the location of placement of the energy tells you whether it's in or out. Hey, it's product, energy was released. Hey, it's a reactant, energy went in. But once you take that energy off an equation and say like, hey, the combustion of methane, that produces 890, you've got to include the sign there. So normal sign conventions for energy transfer apply to a thermochemical equation. Okay, so it's as simple as enthalpy is the energy of a chemical process. We can report that in an equation. Given the idea that energy is conserved just like mass and matter is, when we see a thermochemical equation, what we're saying to you is how the energy is relating reactant side and product side. So when I see an exothermic reaction, what I know is over the course of breaking the reactants bonds, right, putting energy in to break them, and making the products bonds, so releasing energy as we make those new bonds, some amount of energy was either released in that process or taken in. So in an exothermic process, what that means is the products, when they were made, they have less stored energy than the reactants did, right? They have that methane reaction, they released 890 kilojoules that didn't go back, that didn't get used up, essentially. It got released into the surroundings. So when I put in the energy to break the bonds, and then I gave energy back out to make the bonds, basically I had a net release of 890, meaning those two products had less energy in them than the reactants did. And when instead you have an endothermic process where we have to add energy to the reactants to make the products, that now means the products have more energy. Because on the reactant side, just with that water, you need 242 more kilojoules to make the product. So when we put energy in to break the water, and then energy is released as we make them, we don't have a net gain of energy anywhere. We actually had to put energy in because those bonds in the product needed more energy than their reactants even had. Okay, so that's one thing to consider in these processes is energy is conserved. So when we put energy on one side, essentially we're trying to make that side equal the other side. Okay, so energy is a factor that we need to consider. These are all chemical reactions on the screen. We can also write a delta H process for dissolving something, for example. So heat of solution is the process associated with the dissolving process. So that make and break of old IMFs, new IMFs, endo or exo, depending on that make break, right? If we put more energy in to break them than we get out when we make them, we're endothermic. Vice versa for exothermic. So when you see an energy like these on the board, essentially these are the process, this is the amount of energy associated with the process of dissociating into its ions. So for that first heat of solution one, for example, when I take HNO3 and allow it to dissociate into its ions, this is the amount of energy that's produced. For the other one where there's a positive heat of solution, it would end up being a reactant amount then, because that's the amount of energy gained. We can also do something similar with the heat of phase changes. So phase changes we don't think of as chemical processes, but now that we understand IMF, we can still see how there are things being broken and made during a phase change. In order to go from a solid to a liquid, I need to break IMFs, and there's an energy associated with that process. So here are the words we use when it comes to phase changes. We've been pretty non-specific about phase changes up until now in terms of language, but you're going to see here specifically a couple terms that you know and some that might be new. Most common new one for people would be that solid to liquid is called fusion, which doesn't make a lot of sense in our brains. But when we see delta H of fusion, that is the heat associated going from a solid to a liquid. So right here on the screen, that going from water solid to water liquid, the heat of fusion in that case is 6.01 kilojoules per mole. So per mole that liquefies, I need to put in 6.01 energy to break enough IMFs to make that process happen. That's it in terms of the main concepts for enthalpy. Again, main concept is that enthalpy is just heat associated with that potential and kinetic of the system. Here we're talking about chemical processes, so dissolving, phase change, and chemical reactions. Depending on where the energy is placed, it's either endothermic or exothermic. If it's a product, it's out. If it's a reactant, it's in. And you can compare the energies of the bonds depending on whether it's endothermic or exothermic. That's it. Have a nice night.